Okay, so we are talking about section 8.4, where we are dealing with other convergence tests. These convergence tests are designed to deal with a series where the terms are not necessarily all positive. Okay, and we learned about the alternating series test as a test we can use for alternating series to establish convergence. We learned about absolute convergence. That's where we take terms of a series and we take the terms of a series and make them all positive by inserting absolute value signs. And then if that series with the absolute values of the terms converges, then we say the series converges absolutely. And so that series would have to converge as well. Now, series B, you might notice it looks a little complicated. Okay, so series B, if we look at the nth term, the nth term is n cubed over 3 to the nth power. So this is B sub n. So if we were to use the alternating series test, we'd have to show that the n plus first term is less than or equal to the nth term. I'm talking about this, part here, B sub n. And then we'd also have to see if does B sub n approach 0? Does the, hold on. Do the terms of the series approach 0 as n goes to infinity? This is not easy to determine because this based on n cubed over 3 to the nth power. Not an easy. The alternating series test, the conditions are not easy to establish. So what we're going to do is we're going to bring in another test here that we call the ratio test. So I want to bring that test up from the ebook here. So let me find it here. One moment. Here we go. Just give me a moment. I have it here. Ratio test. I think you're going to like this test. Okay, so this is the ratio test. The following test is very useful in determining whether a given series is absolutely convergent. And remember, if the series absolutely converges, then it converges. So establishing absolute convergence of a series is great because then it means the series itself converges. So, okay, by number 1, it says if you take the absolute value of the ratio of the n plus first term to the nth term, and that limit as n goes to infinity equals L, and L is less than 1, the series is absolutely convergent and therefore convergent. Okay, the second part here, so let me just, hold on, can I highlight? Give me one moment here. I want to highlight the first 2 parts here. The second part here of the ratio test says if you look at the ratio of the n plus first term to the nth term, okay, so that would be look at the ratio of a term divided by the previous term of the series. If it equals L and L is greater than 1, then or if the limit equals infinity, the series is divergent. Now, what are these in the ratio test? The conditions 1 and 2. What do they remind you of? What are those L being less than 1, series absolutely convergent. L being greater than 1, series divergent. what is this? What does this kind of remind you of? Well, what series have you seen where you know, when you take the n plus first term and divide it by the nth term, you're looking at a ratio. What kind of series have you experienced before when the ratio is less than 1, the series, or the absolute value of the ratio is less than 1, the series converges, and if the absolute value of the ratio, or common, well, just to say absolute value of the ratio greater than 1 series diverges. That's right, Jonathan, geometric series. So what you're doing here is you're trying to basically see if your series, if the terms of your series, as n gets large, if the terms of your series, you're trying to see if the terms of your series behave like a geometric series. Because remember, a geometric series, the common ratio is found by taking a term of the series and dividing it by the previous term. And in conditions 1 and 2 of the ratio test, that's what you're doing. But because you don't have a geometric series to start with, there's not a common ratio between the terms of the series. However, if you take the limit of the ratio of the terms of the series and you get a constant value L, then you can say that your series eventually behaves like a geometric series. And based on whether that limit L is less than 1 or greater than 1, you can establish if your series converges or diverges. Okay, that's the beauty behind the ratio test. The third part of the ratio test says if the limit of the ratio equals 1, the ratio test is inconclusive. So this means that the ratio test doesn't always work. Okay, so this is a type test you want to use if nothing else works. If you've learned now, you've learned between the three, sections 8.2, 8.3, and 8.4, you learned a lot of ways to determine if a series converges or diverges. But if none of those ways works, you try the ratio test. So if we go back to our series here, okay, if we go back and look at series B, well, I'm going to try to use the ratio test on that series. So, okay, let's go ahead and look at the solution. Here we are. So for part B, for this series, none of the previous tests we learned can be easily used. Okay, none of the previous tests we learned can be easily used to establish, and forgive me here, let me just highlight all this. None of the previous tests we learned can be easily used to establish convergence or divergence of this series. Therefore, we're going to try the ratio test, and we're going to let A sub n be the term of the series. Okay, so let me give you a moment to get caught up to here. Okay, so we need to, well, first of all, we look at the ratio of the n plus first term to the nth term, the absolute value, of course. So in this ratio, I write in the denominator the nth term of the series. Okay, not hard, right? To get the n plus first term of the series, I substitute in an n plus 1 everywhere I see an n. So you notice if you look at this term here in the numerator, every n value in the denominator, I put in an n plus 1 for every n value. And that gets me my n plus first term. It makes sense, right? It makes sense. And now what we have to do is we want to find the limit of this ratio. But in order to do that, I have to simplify the ratio. Well, you learned, right, of course, that a divided by, hold on, if you have a divided by b divided by c over d, okay, that just equals, hold on here, hope I have room, that just will equal a over b times c over d, right? That's a rule you've known a long time. So that's what I'm doing here. I'm taking the reciprocal of the denominator and multiplying the reciprocal of the denominator by my numerator. Given that I have to compute the limit of this expression, it makes sense to group together like terms. So I have a negative 1 to the n plus first power here and a negative 1 to the nth power here. So let me just put those above, together. Hold on, Jonathan. Let me see. This second fraction here is upside down. This fraction here in the so I'm taking a fraction and dividing it by a fraction. So can you show me, Jonathan, where you think there might, oh, Jonathan's right. Thank you, Jonathan. This should be D over C. Thank you. Yep, thank you. Thank you, thank you. Very good, very good. So, right, I have the reciprocal here, and I'm multiplying by the reciprocal, and I'm going to group together like terms. Okay, so n plus 1 cubed, and n cubed. There's nothing wrong with putting that over here. And then 3 to the nth power on top, 3 to the n plus first power on the bottom. I'll group that here, just to make my life easy. So of course we want to simplify everywhere we can simplify. So I'll show you the simplification, but let's just, what would negative 1 to the nth plus first power divided by negative 1 to the nth power be? What would that equal? Negative 1 to the n plus first power divided by negative 1 to the nth power. What do we do with the exponents? What do we do with the exponents? Bases are the same. We subtract the exponents, right? That's right, Jonathan. And so this would give us negative 1 to the first power. Okay, so I'm just trying to, this negative 1 to the n plus first power divided by negative 1 to the nth power is going to equal negative 1 to the first power. Let's take a look at 3 to the nth over 3 to the n plus 1. Let's take a look at that. Okay, that's going to equal 1/3. Okay, that equals 1/3. Please let me know if you're comfortable with what I'm doing here. Another way you can think about it is 3 to the n over 3 to the n plus first power equals 3 to the n over 3 to the n times 3 to the first power. And the 3 to the n powers simplify out, giving you 1/3. That's another way to think about it. You probably like that way a little. How many like that way a little better, as opposed to subtracting the exponents? Okay, that's good. All right, Jonathan. So, see, this is what I would do in a face-to-face class. I would elaborate on what's there on the paper. I teach a face-to-face class, and I actually use slides just like this, but I elaborate just like I'm doing here. So, okay, so let us move to the next page if we're good. Who's good so far? Give me a thumbs up if you're good so far. Okay, Clay is good. All right, hold on here. Clay is good. Let me see here. Let's see. Gabriel, how are you feeling? Are you comfortable so far with the ratio test? Franklin, how about you? Franklin?
Yes, Professor, I'm okay.
You're good. All right, all right. Victoria, how about you? Are you comfortable?
I'm just looking through the material, but I'll have to review it.
Okay. All right. All right. All right. Well, let's keep going with the ratio test then on the next page. So the ratio simplifies to this, and this is just simple math, really, that I'm doing here. The absolute value of -1 becomes positive, so the absolute value, the -1 goes away, and n plus n, this here can be written like this. So then you get to here. The absolute value of the ratio is 1/3 times the quantity 1 plus 1 over n to the third power. And as we let n go to infinity, this is another way, we're going to let n go to infinity, the 1 over n is going to drop out, right? And so, 1 over n will go to 0 as n goes to infinity. So this ratio will approach 1/3, okay? And that's the L value, and that's less than 1. So therefore, by the ratio test, this series is absolutely convergent. An absolutely beautiful, and hence convergent, an absolutely beautiful, beautiful type of test, the ratio test. Okay, take a moment to copy that down. Are there any questions so far? All right, well, then let's add so I want to just, okay, so by the ratio test, the series is absolutely convergent. And I want to just, give a little interpretation here. This is not necessary, like what I have written here is, we've solved the problem, but I think it's helpful that you see just an explanation of sort of to give you an intuitive feel of what's going on. I'm sharing with you what's going on in my mind when I do these problems. But the later terms of the series, this series where we have the absolute value of the terms, will behave like a convergent geometric series with a common ratio of a third. So that series will eventually act like a convergent geometric series with a common ratio of a third. Because of that, that series has to converge. Because it's not how the series behaves in the beginning that determines convergence. It's how the series eventually behaves, right? It's a little bit like, I don't know if you've seen the movie Star Wars with Darth Vader. I don't remember. That was made before your time. The first three, like back in the 80s, in the 70s. I don't know if you've seen Star Wars, but there's a character called Darth Vader. How many have heard of Darth Vader? Okay, Clea has, Susanna has, and all right, and even the new, yeah. So Darth Vader was like a bad guy, right? But in the third installment, eventually, he's a good guy. You know what I mean? So he eventually was a good guy, and so he was good. I don't know. I just like to think of analogies. This series eventually acts like a geometric series with a common ratio of a third, so it has to converge. And so therefore our series converges as well. I think that's a pretty good analogy. Well, I don't know. What do you think, Clea? Does that do it for you, or do you have to think on that more? Think more. Okay. All right. All right. All right. That's fine. Math is like life a lot of times. Or have you ever seen those movies where the person in the movie is like a good guy, good person in the beginning, and then eventually they become they're like a bad guy? How many have seen movies like that? Let's do that. In the beginning, the person's good, and then yeah. So Victoria, the person became like, eventually in the end was bad. So it's kind of like this series is the same kind of thing. How the terms of the series act in the beginning when n is small, the first billion terms of the series, whatever, how the terms of the series are behave in the beginning doesn't matter. It's how they behave eventually, and that's so. I think Victoria likes that analogy. I think that's hopefully good there. Okay, so now you have learned in section 8.4 about some different convergence tests for these series where not all terms of the series are positive. And as always, if you have a convergence series, you want to be able to estimate the sum of the series. You want to estimate the sum of the series. So let's talk about what's called the alternating series estimation theorem. Okay, so I'm going to move to our next example here. Are there any questions before I move forward? Okay. Okay. So I'm going to blow this up a little bit. Now, this is in your book. This is in your book. It comes before example 4. It's called the alternating series estimation theorem. Okay. And what does this theorem do? Well, it's going to allow us to estimate the sum of a series. So it says that if you have a sum of a series that satisfies these two conditions, conditions 1 and 2, then that alternating series converges, because those are the conditions that are required by the alternating series test for an alternating series to converge. If that's the case, then the R sub n, which is the remainder of the series, the absolute value of the remainder, which equals the sum of the series minus S sub n, that'll be less than or equal to the n plus first term. We can phrase it another way. We can phrase it another way. Sorry, one moment. Okay, everybody. Thank you. Thank you. All right. So here, come on, get that off. Okay, so I'm taking the difference between my series and the nth partial sum, right? That's what S sub n stands for, the nth partial sum. And we denote often the sum of the series we denote by S. So the difference between the true sum of the series and the nth partial sum is called the remainder. And you saw that back in section 8.3 with the, what was it? The remainder estimate for the integral test. So by the alternating series estimation theorem, the remainder, or the error in estimating your series with the nth partial sum, would be less than or equal to the n plus first term of the series. Okay, and this basically, if you go back and look at that picture in section at the beginning of section 8.4 in figure 1, I think you'll intuitively see why this has to be true. But I have a little example to help you feel comfortable with it. I have here the alternating harmonic series, okay? And that series is our series, and so we'll call that our series S. We'll use S to denote that series. And I'm saying, let's suppose I write out the first 4 terms of the series. Okay, I write out the first 4 terms of the series plus the remainder. Okay, so the if you take the, I mean, if you have the sum of the series minus the 4th partial sum, okay, that's going to equal R sub 4. So that means S would equal S sub 4 plus R sub 4, which is what I have written, you know, here. This is S sub 4 plus R sub 4. Now, R sub 4, if we look at the absolute value of this remainder, it has to be less than 1/5, which is the next term, right? It's the 5th term. And it has to, because if you take a 5th minus a 6th, that's going to be less than a 5th, right? A fifth minus a 6th is less than a 5th, certainly. Well, a 5th minus a 6th plus a 7th would have to also be less than a 5th, because a 7th doesn't make up for the difference, right? So that's just I'm trying to, does this give you an intuitive feel of why the alternating series estimation theorem is true? That's what I'm hoping it'll do. All right. All right. So we need to look at an example of this problem. So what I want to do is I want to go to the, I think I want to go to the ebook. Let me just see here. One moment. One moment. Yeah, I'm going to go look at example 4 with you. So into the ebook here, one moment, let me get it here. Okay, into the ebook we go. Okay, there's that alternating series estimation theorem. Okay, and in example 4, they want you to find the sum of that series correct to 3 decimal places. Now the n has an exclamation mark by it. What does that mean, that exclamation mark? Factorial, that's right, Susanna, a factorial. Okay, so let me go to the whiteboard here. And, you know, factorials, it might have been a while since you've seen those, but you're certainly going to see them now. So 0 factorial is defined to be 1. 1 factorial is 1. 2 factorial is 1 times 2, and that's 2. 3 factorial is 1 times 2 times 3, that's 6. 4 factorial is 1 times 2 times 3 times 4, which is 24. And incidentally, 4 factorial, you can also think of it as 4 times 3 times 2 times 1. And it does approach infinity fast. It sure does, Jonathan. How many have seen, and then we can keep going with this, how many have seen these factorials in perhaps another class, another math class, or another science class? Okay, OPME's seen them. Okay. And hold on here. One moment here, everybody. Sorry. Sometimes, so another person answered. I didn't see it because it showed up on the participant thing. I didn't see it. Franklin, have you seen it before? Factorials?
Yes, Professor.
Good, good. Okay. Well, they're very important for our chapter 8. Very good. So let's get back to the problem then. Okay, so they basically in the beginning, they say that, I mean, like this part here, I don't know if I can, maybe I'll put it in pink. They're just establishing here that this series, the terms of the series, disregarding that plus or minus, the terms of the series get smaller, they decrease, and the terms of the series approach 0. So that means this series is going to converge. So it makes sense then to, by the alternating series test. So it makes sense to then ask to estimate, hold on here, it makes sense to ask this question, find the sum, correct the 3 decimal places. It makes perfect sense. Hold on, let me just get this off here. I got too many. Good, that'll make my life easier. Okay, so, all right, well, what we have to do is we have to, notice the series starts at n equals 0. Notice the series starts at n equals 0. So let me go to the whiteboard again with you here. And for this example 4, here's the series. N equals 0 to infinity of -1 to the nth power over n factorial. So the first partial sum, they call it S sub 0 because you're just looking at the first term when n is 0. See? And you get 1. So you're used to partial sums like starting like the first partial sum is S sub 1, second partial sum is S sub 2, and so forth. But you know, you're smart, everybody in here is smart, and you can say, okay, well, the first partial sum I'll call S sub 0. It's a little more convenient, right, to say that, because you know, the series starts at n equals 0. Then S sub 1 would be -1 to the 0th power over 0 factorial plus -1 to the first power over 1 factorial. Okay, and that would actually be equal to 1 minus 1, and that's 0. Okay, if we did one more, the S sub 2, which is the third partial sum, that would be -1 to the 0 over 0 factorial plus -1 to the, well, let me put it over here. I don't like being, I like to have space. I like to have space. Let me do S sub 2. That, in this case, would be the sum of the first 3 terms of the series. So that would be 1 minus 1 plus 1/2, and that would give you a half. Okay, so just to kind of get you comfortable with what they're showing an example for in the book in the solution. Okay, are there any questions so far? Okay, well then let's get back to the solution in the book for example 4. So okay, so what they do is they write out this the series. They write out the first 8 terms of the series. Okay, and again, we want to find the sum of the series correct to 3 decimal places. Well, so what we want to do is we want to stop when we have a term that's less than 5 over 10 to the 4th power. Okay, now let me just go to the whiteboard here. So you see what they've done. The factorials, they've converted the factorials into numbers, and then they like when they get to this b sub 7 part, they do it a little differently than I would do it. Okay, but let me just hold on just 1 minute here. Okay, just doing something on my calculator. Yes. Okay, so let me finish this up on the whiteboard. So for this problem, okay, so the 7th partial sum is 1 minus 1 plus a half minus a 6. Again, this goes with example 4 from section 8.4. So we have 1 minus 1 plus a half minus a 6 plus a 24th minus 1 over 120 plus 1 over 720 minus 1 over 5040. Okay, and that's the 7th partial sum, but actually let me just call it the actual sum, and then add in, okay, the series keeps going. Okay, so let's take a look here at thank you for your patience here. So this is b sub 0, this is b sub 1, b sub 2, b sub 3, b sub 4, b sub 5, b sub 6, and b sub 7. Now, the 6th term, 1 divided by 720, 1 divided by 720, this 6th term equals 0.00138. The 7th term, 1 divided by 5040, is equal to 0.0001984. Okay, approximately. All right, so correct to 3 decimal places, correct to 3 decimal places means that this means we want to find B sub n such that it's less than 5 over 10 to the 4th power, because it's 3 decimal places. So just like with the example we did in section 8.3, we put a 5 in the numerator and then 10 to the 4th power, because 4 is 3 plus 1. Well, 5 over 10 to the 4th power is 0.0005. If you take 5 and divide it by 10 to the 4th power, you get 0.0005. Well, this term here, B sub 7, 1 over 5,040, this is less than 5 over 10 to the 4th power. That's less than 5 over 10 to the 4th power, because that term is equal to 0.0001984, and that's less than 0.0005. Therefore, the sum of the series, correct? The sum of the series. I don't know why. Hold on here. Sorry. Sorry about that. I'm almost done here, class. I know I'm a few minutes over. This means then that the sum of the first 7 terms will be sufficient to approximate the sum of the series correct to 3 decimal places, the sum of the first 7 terms. Okay? So this is how I'm applying the alternating series estimation theorem. And if we go back to now the example, okay, they do it a little differently, but they say here that the sum of the first 7 terms will approximate the series to the accuracy we want. And they're bringing in a 0.0002. I don't know why they do that. You don't need to. Okay, so that's how you use the alternating series estimation theorem. Are there any questions on that before I stop the recording? Who's at least somewhat comfortable? Give me a thumbs up if you're, I mean, I know you're not completely comfortable, but are you somewhat comfortable? Give me a thumbs up if you're somewhat comfortable, because I'd like to at least know that, who's 50-50 right now? I know you need to practice. Okay. Jonathan says he's glad this is recorded. Yes, you want to go back to the recording. This last part will be very, very helpful. And well, the whole thing's helpful, right? The whole lecture. So on that note, I'm going to stop. And you know, there are help aids for your section 8.4 homework, which is due Monday. There are help aids, and this what we went over in the lecture. I'll make the recording available under the course content. And let me go ahead and stop the recording.